Okay, hi everyone. I'm João, and this is Bertil. We're going to talk about A/B testing. Far-fetched, there's a T missing. Sorry about that. Okay. Okay, so this presentation is about A/B testing, also known as double-blind randomized controlled trials. Okay, so we're going to look at Python code. The repo is on the Slack channel. If you want, you can download it and start playing around. More specifically, in A/B testing, we're going to talk about what to do if you have a small sample size. Okay. Okay, so first we're going to see how you run a test. Then for this presentation, we're going to use some generated data. So the idea is that you use this then on a real data set. We're going to see how to process the results. Then we're going to talk about A tests. I will specify better what there is. Sensitivity testing. How to process the source data set, and then all the complications that come from having a small sample sizes. Okay. So why would you run an A/B test? So an A/B test, the simple idea is, for example, on a website, you want to implement something new. Let's say you have a button that is red and you want to see if it was blue, would people click more? So basically what you do, you divide the users on your website, 50% see the blue, 50% see the red, and then you compare to see which one performs better. So that's in a nutshell, that's the idea. Okay, and why would you do this rather than simply having the original and then change to the new version and then compare one with the other? Because maybe you have, for example, seasonality, so you cannot compare different periods in time, or you can have several different changes happening at the same time, so you want to have multiple experiments, and so again, you cannot implement one and compare and implement another and compare. That would take a long time, so you want to do everything at once. For the small samples, so if we're talking, for example, about a website, you typically have millions of users, but maybe your website is it's smaller, it's more specific, so you have few users. It can also be applied, for example, on clinical trials. In the beginning, you probably have very few patients. You're going to test with very small sample to then increase your sample. Or, for example, in a company that is business to business, so typically you will have like a few customers, not millions of customers. Also, you can, when, let's say that you have different locations. For example, you have physical stores. And in each physical store, you cannot show different things to people because people are there, so they are going to see it. So let's say that you have, for example, a fashion store and you have a certain collection or another collection. You want to see which one performs better. You cannot show half the customers one and half the other because all of them will see it. So you have to split things by store. So that's the clustering part that we are also going to look at. And so, does it actually make sense to test on a small sample size? It does make sense, but you need to understand that you're only going to be able to measure if the difference is quite large. To test small differences, if you have a small sample size, you're probably not going to detect that difference. So you need to manage the expectations with the stakeholders. That's if you do have a small sample set, you cannot understand small differences. Okay, so as I was saying, the code is on, you have the link on Slack, so it's free to use. It uses just basic, simple libraries. In this case, we're going to actually use a t-test, which is quite simple way of doing this. So the idea was to focus more on the problems with the sample sizes. And so we're not going to use, for example, Bayesian approximation or other Bayesian framework or other type of framework. You can, if you download the repo, you can run most of the things. Just one of them takes a little bit of time to run. Okay, so let's go to the tests. Okay, so if you run an A/B test, the first thing you need to do, and this might seem simple, theoretically speaking, but if you actually do work on this on your day-to-day, it's actually not that simple. It's a very tricky part, which is to define your test. So you need to define first your population. Again, with the example, if you have a website, let's say that you want to make a change on the checkout of the website, then your population are the users that go to checkout, okay? Then you split in treatment and control. So control will see exactly the website as it is right now, and treatment will see a different version, typically a small change. Then you have to define an objective metric. For example, in this case, it would make sense to be the conversion rate of the website. So if people are buying more or not, so you want to improve your sales. This can also be very tricky to define a metric that is relevant to your business. Sometimes it's not that obvious as sales, or sometimes it is difficult to measure sales if you're doing something, for example, on your homepage, and it takes a while to go through all the steps until checkout. So maybe if you do a change on the homepage, you will not detect something so further away on the funnel. So it's kind of tricky. And the other thing is the minimum relevant impact. So this is basically what difference is relevant to you. So let's say that you have an e-commerce site and you have an average order value of 30 euros, for example, okay? So on average, each item that people buy costs 30 euros. If you increase to 35 euros, then that's a relevant change. But if you increase to 30.001 euros, then nobody cares. So you need to define this minimum relevant impact, and this is important because with this you can define your sample size. So to detect a big difference, like from 30 to 35 euros, you need a smaller sample size. If you want to detect a very, very tiny difference, like the 30 to 30.001 euros, it would take a really, really large sample size, and it would take, depending on the traffic of your website, it would take years to reach a conclusion. So it's important to define how much are you willing to wait to detect the difference that you consider to be relevant. Okay, so this is the basis for a t-test. So as I said, it's the simplest test that you can do. So essentially, you need 4 numbers, okay? So you have the conversion rate for treatment and for control. Again, treatment is seeing exactly with no changes, and control is where you apply the change. And to define this conversion rate, you need the number of observations and the number of conversions. So for example, this can be the number of users that went to your site and the number of people who clicked on the button. From here, you calculate the variance and the standard deviation. Okay, so this is just a few equations, but it's simple, okay? All right, so then you do an hypothesis test, which is you define your hypothesis. So in this case, the null hypothesis would be that treatment and control are the same. There is no difference between them. And then you try to falsify this hypothesis, okay? So you try to prove that, in fact, there is a difference between them. To do this, you define an alpha, which is so your threshold to make a decision. And if you conclude that the odds that control and treatment are the same is less than your threshold, typically 5% or 10%, then you conclude that, okay, they are different, or at least there is a very small probability that they are the same. So most likely they are different, and you define a threshold to then make a conclusion. Okay, so coming back to the minimum detectable effect. So this is the effect that you can measure, okay? So basically, for this calculation, you just have to assume that the observations on control and treatment are roughly the same. And you compute a conversion rate based on the conversion rates of your control and treatment. And from here, you get the minimum detectable effect. So in practice, there are two ways of doing this. The first way is to say, okay, I have, let's say, 1 month to run this test. This is the time that I have. I don't have more time. And the traffic on my website is this number of users per day. So I have this sample size. And with the sample size that you have available, then you calculate, okay, I will be able to measure differences of 1% or 2% based on the amount of the sample size that you can get. Or you can do it the other way, which is to say, okay, it is relevant for me to measure 0.5%. That's still relevant for me. So I will have to wait this amount of time, 2 months, okay? But with this, have in mind that it's not linear, okay? So if you want to detect a difference of 2% and it takes 1 month to collect the data, if you want to detect half of that, if you want to detect 1%, it will take, so half, it will take 4 times more, okay? So it's not linear. So the lower you want to detect, the smaller effects you are going to be able to detect, the longer it takes, and it's exponential. Okay, so essentially, we compute the p-value, and so the p-value, in simple words, it's the probability that control and treatment are the same, and if the p-value is below the alpha we defined, then the test is significant, and we can conclude that there is a difference. Okay, so again, we are using the frequentist approach. There are other approaches. The Bayesian is very, also very used. Here we are just using a simple t-test. Okay, so this test is valid for proportions, okay? So that means that each observation can only have a maximum of 1 conversion. So let's say that we're talking about clicks on a button. What you can define the metric is, so the observation would be people who saw the button, and the conversion would be someone clicked on the button, yes or no. It cannot be number of clicks, because that way the conversions would be higher than the observations. Okay, so it always has to be a proportion. It has to be binary, so yes or no. And also you have to make some approximations between a Bernoulli sample and the Gaussian. So for that you need theoretically at least a sample of 30 observations, which is not a lot, it's okay. And your conversion rate needs to be a little bit above 0. So here it says far enough from 0, but it's just a little bit above 0, it's okay. And also, all your observations must be independent. So let's come back to the example of the physical store. If I have a physical store and I am doing something different with my clients maybe are going to talk to each other and influence each other. So they are not independent. And in the physical reality, that's very important. Or for example, if you're doing something in a city and doing something in a different city, inside each city, people will talk to each other. So there's that problem too. Okay, so now we're going to look at the code. So the first thing that we're going to do is to actually generate random samples, okay? So here, this part is simply to generate a random date time between these two dates, okay? So we generate a random date time. We then generate a conversion, observation and conversion. So basically, with this function, you end up with a timestamp that is randomly created, a user ID, and then if that observation has a conversion, yes or no, and what is the delay to that conversion. So if the person visits, for example, if the person visits the website at a certain time, after how much time did it convert? From here, we compute the conversions. So basically, the observations that had conversions just compute the time. And we end up with a table like this. That's if I don't know how many of you work in e-commerce. Okay, so you probably have seen something like this. So a timestamp, a user ID, and then here it says observations conversion. So this would be something like a visit to the website and someone purchasing something. Okay, so you probably have a table like this somewhere in your database. And then when you run an A/B test on a website, typically what happens is that internally you have a software that splits users to control and treatment, and it shows them a different version of the website, which is what is being done here, but fake. Okay, so we attribute each user to its either seeing control or treatment. And that's it. We have our data set that we can then apply this to a real data set. So let's start actually processing the tests. So the first thing you need to do is take all your events and group them to end up with the four numbers that we talked about. So for control and for treatment, observations and conversions. Okay, so here we can see we have 228 observations and 116 conversions for control. Okay, this is just, okay, we just a function to make that. And then we're going to compute the statistics, so the conversion rate, the variance, and then compare the difference between control and alternative with your confidence interval. So the confidence interval is a tuple. So if the difference is smaller than the lower limits of that confidence interval, then the treatment loses. It's worse than control. If it's the opposite, it wins. If it's in the middle, then there is we cannot conclude that there is a difference between control and treatment with the sample size that we have. Okay, so we create the class t-test that basically takes these totals. You input an alpha, typically 5% or 10%, and you compute all that we've been seeing so far, and you end up with all these values. Which is a lot of stuff, so we just put it in a sentence. So take all those values and make a sentence with it. So on these tests, basically we can see that the metric went from 49 to 53%. So the difference is 4%, and it's not significant. Okay, so we cannot conclude that there is statistically a difference between control and treatment. And so we have our class A/B test that essentially takes the events, takes the segments, which is who is on control and on treatment, and then it has units and clusters that we are going to use later. So for now, we are not using this part. And so you can compute an A/B test given the events. and print your decision. Okay, so as we talked before about what is the minimum difference that you can measure given your sample size. So here are some practical examples with this specific metric. So this is will not give you exactly always the same result, but you can get an idea. So if you have 1,000 observations, you can see that you can measure a difference of 7.8%. If you have 10,000, 2.5%, and 100,000, 0.8%. So you can see that to go from approximately 8% to 1%, so that would be 8 times less, but you had to go from 1,000 observations to 100,000 observations, so that's definitely not 8 times higher, it's 100 times higher. As we said, another type of test is the sequential test. So we have a t-test, we also have a Bayesian test. This is another kind of test. This is actually the one that we have in production at Farfetch. It has some very interesting features because you actually don't need to define the minimum detectable effect. You can run the test as long as you want. And look at the data how many times you want without increasing the false positive rate, which we're going to talk next, but it's very interesting way of doing tests, and we can talk more about that in the end. We didn't have time to put everything in the presentations. So now I'm going to talk about A/A tests. So an A/A test is basically the same thing as an A/B test, except that control and treatment are seeing the same thing. So it's a complete waste of time because you're not concluding anything, you're showing the same thing to two groups and trying to conclude which one is better. So why would you do that? Basically to control the quality of your test. So if you do show the same thing to two groups and you conclude that one of them is doing better than the other, then your test is not very reliable, okay? And we can look at this by doing a confusion matrix. So if you have a test and the result gives you that there is significance, there is a difference between control and alternative, but in fact there isn't, then that's a false positive. If there actually is, then that's a true positive. And the same thing for the non-significant results. So with the A/A tests, what you can measure is the false positive rate. So you know that there is no real difference because you're showing the same thing to one and another. If you conclude that there is a difference, then that's a false positive. Okay, so basically what we're going to do is take that, I'm talking about websites, but you can use it for something else. So take data from your website from the past 6 months, randomly split between control and treatment n times, and so you end up with n A/A tests. Okay, so we're going to do a batch of A/A tests. So we do this splitting, and we do this, in this case, 100 times. Okay. And then essentially you aggregate the results from those A/A tests that you did. So the sum of the tests that were significant, those are your false positives, and the number of tests is just the count. Okay, so you end up with something like this. So we run this 4 times. The first time in 100 tests you had 10 false positives and so on the others. And we can already see that it's not deterministic, okay? You can have different results if you run this several times. And so we asked the question, okay, let's say that one of these had the results of 7 false positives. The 7 was because there was actually a 7 here, but as I said, this is not deterministic, so now it's a 10 there. So 7 false positives in 100. Is that okay or not okay? We defined an alpha of 10%, so we should have 10 tests. But as we can see here, it varies a lot. So what can we do about this? So let's check the alpha. So essentially what we do is treat this aggregation of the A tests as if it was a test. So we do a confidence interval on those tests, okay? And we end up with a confidence interval rather than a number. So rather than saying 7 tests, we say, okay, between 9.4 and 12.6. So we define an alpha of 10. So far we are okay, but the range is very large. So what we can do is rather than running 1,000, let's run 10,000 and see what happens. Okay, now the false positive rate is between 9.7 and 10.7, and we have an alpha of 10%, so apparently everything is okay. So just sanity check, your code is working okay, it's doing proper A/B testing. But we can also use A tests for other things, and we will see that next. Another way to actually look at the A tests is to plot the p-values and the t-values. And you should end up with something like this. So if you look at the p-values, it should be a uniform distribution, so that you get alpha percent of the tests have an alpha inferior, have a p-value inferior to alpha, okay? So if it's a uniform distribution, you're going to end up with 10% below the alpha if you define the alpha as 10%. And the t-values should give you this normal distribution. Okay, so now we're going to look at sensitivity tests and what comes next, and this will be Bertil. For this part, questions? Yeah.
When you were collecting the data at the beginning, there was the last column, which I think collected the time that the person took before they converted, and I was expecting perhaps how you would use that column, but I didn't see it. Maybe I missed it.
Oh, okay, so here, sorry, let me see, generate random samples. Okay, so here you have an event time and the delay that it takes to convert. And then what you do next is you take the observations that had a conversion. So if the conversion is true, for example, the index 3, the conversion is true. So you take that line, you take the event timestamp and you sum the conversion delay, and you end up with the timestamp for the conversion. Okay, so
if the number wasn't within the confidence interval, how would that guide your design?
So if it wasn't in the confidence interval, then something would be wrong, and you can start digging in. For example, as you were saying, you could check if your observations are not independent, if there's actually something wrong with the code, if there's a problem with your data, if you're doing this with real data. Or if for example, one of the things that can happen is a very big change of behavior. So let's say that your data is corrupted and at a certain point everything is a 0, so there are no more conversions from that point on, things like that. So you can start check those things, for example.
So historical want to change, can I compare them or no? And if there is a difference between two stores, can I still run the A/B test afterwards, but somehow take the previous data to...
Yeah, actually, Bertil is going to talk also about the segmentation part, so Maybe you can...
So I won't cover that specifically, but I can answer your question right now. If you know that there's certain types of stores that behave differently, then you want to run A/B tests separately on each of those types, which means that you're reducing your sample size, which is going to be a problem in terms of significance and things like that. You can try to find a metric that is the same for all stores. Retention, for example, might be a good example for that. But this can be a source of concern. There's a piece of code which is not going to present now, but which is in the notebook, which is hidden on that presentation. That covers that a little bit. The problem is less when you have different types of stores that have different conversion rates, but when that conversion rate is correlated with the scale of the store, in which case then doing an A/B test then becomes a little bit trickier. So there should be some answers to that in the notes. Just when we presented that, we presented to some of our colleagues that had a ton of questions. So this took about an hour to go through. I feel like we're doing really good on time. So I'll get into more details after that. That's one of the kind of stuff that becomes difficult when you actually do a test in real time, as opposed to what we're doing now, which is on simulated data. There's a lot of things that you see in the test that actually don't make sense for this presentation because they come in later in the test. So defining user sessions as opposed to just users, defining people who log in and log out, so we know who they are but after the fact. That kind of stuff is things that we discuss a bit in the hidden part of the presentation. But yeah, absolutely, all these things are painful, all these things are real, and this is just an overall methodology for you, if you know there's a pain, to know if that pain is actually hurting your test quality. Does that make sense? Just to summarize a bit, so what we've been doing so far. So far we've been doing what is test in general. So we define a t-test explicitly, but anyone who's familiar with Bayesian test sees like, okay, a test can be positive and negative, and that's what we care about. We have a false positive rate, which is the universal thing that all the tests have to have. You want to look at anomalous behavior, but sometimes there are anomalous behavior without difference. And those anomalous behavior are something that we can control for. That's the alpha that we've been talking about so far. Happy to ignore the generate random samples because that's kind of an ad hoc thing for this presentation. More than happy to discuss about your own data. If you have right now on your laptop access to your company data, feel free to use the code that is in the repo to just run that data through the AA test and see if you have the same alpha that you set in the test. You can set it at 1%, 2%, 5%, 10%, 20%. You should have a confidence interval on large AA tests that should match the confidence in the false positive rate that you have. Just out of curiosity, how many people here have downloaded the repo? Raise your hand. Okay, almost everybody. That's amazing. Small repos. Good Wi-Fi. Thank you so much, organizers, for the good Wi-Fi. How many of you are following the notebook as we go through the presentation or the presentation? About a third of that. Okay, cool. Sorry about the quality of the code and sorry about all the typos. I realized looking at that I cannot live without a spell check. So I misspelled the name of my company. So far, so good. Just on the first slide, nowhere important, no one notices. Is it clear in terms of how do we, given data, we get results of that test? Show of hands, that makes sense to everybody? Yeah, cool. Does the point of an AA test make sense to everybody? It was introduced as doing nothing, which I think is a really good way of presenting it, but actually, if you do nothing, you should know what happens. And the fact that 10% of the time something happens is a little surprising, but that's exactly what we intend for. Does it make sense for everybody? Cool, because we're going to go one level above. The problem with AA tests is that you say, okay, I know that if my change is completely useless, 5% of the time, 10% of the time, I'm going to say, oh, this is a great idea, which is not very reassuring. The question is, what happens if you actually have a good idea? So you could try to have good ideas, and notice that your tests are always super positive, but it won't tell you something very reasonable. So what you can do is sensitivity testing. Sensitivity testing is not just something very hard to pronounce. It's also a test with a boost. So you do nothing, and then you fake, which is even worse. The idea is you take two identical samples, just like you do for a test, and you split them just the same way for a test, and then you say, OK, I have control and treatment. I'm going to inflate treatment to make sure that the test is positive. How much do I need to inflate treatment for the test to be positive? And if you can figure out how much you can inflate treatment for the test to be positive, then you don't just control for the 10% or the 5% of false positive rate. You know how much of an impact will be detected by your test, which if you're talking to doctors who are trying to do experiments on clinical tests, or product designers or product managers who are trying to improve the website, or marketing managers who are trying to get more people to use your product. These are actually what they care about. They want to know, okay, I'm trying to do something. I hope that is going to bring in 20% more business. Is your test going to be able to tell me this is the case? So the naive implementation is super simple. You take 0%, 0.1%, 0.2%, etc., down to 10%, 20%, 50%, 100%. So the Q at the end is you triple the impact of your test. So clearly we cover from very small impact to very big impact. And on the A/B test that you have, you define a new method that is given each one of those thresholds. You copy the results of your test, and you say, is that test with that little boost of 0.1%, 0.2%, is it significant? And as soon as it's significant, then you say, okay, that's a threshold where if I increase treatment by that much, I detect that there's a difference. Does it make sense? Yeah? No? Let's look with an example. You have an A test that was handling there in memory. You test, and it's not significant, meaning that test, there's no big difference between that. Very much expected for 90% of the A test. And if you look at, okay, if I increase that by 0.1%, is it significant? No. 2%? No. 10%? No. 20%, that test suddenly becomes positive. So you know that for that A test, if you increase treatment, the conversion rate of treatment by 20%, you're going to detect something. And you define a sensitivity test, which is an extension of the batch test, which is basically rather than run A test 100 times, you run that loop 100 times. You're trying to find what is the effect 100 times. So that's the, you split the test, you compute, you try to detect the effect that you have. And if once you find the effect, you just add it to the list diff. And so you have this list of difference. So it's going to be 10%, 20%, 20%, 10%, 5%. And what you can do is, given a test, you run that, you count them, and that gives you this big list. So what essentially you have is, in this case, out of 100 A tests, 14 of them are false positive. That's the first line. If you do zero change, the test is positive. That's a 14 out of 100. It's a bit high, but it's roughly where we expect it to be. Some of them are very close to being positive, so 1%, 2%. But most of them actually change by a 5, 10, or 20% conversion rate. What is interesting is that for 20% of your A tests, for 21 out of 100, you need to increase treatment by 50% for your test to be like, oh yeah, no, now I see a difference. So this is not very sensitive to change. You need to change dramatically your result for the test to be like, oh yeah, no, there's something there. Does it make sense?
What is the difference with minimal detectable effect size?
Sorry, I need to go to. Sorry, come again?
What is the difference with minimal detectable effect size?
So there's clearly something about minimal detectable effect. You sense that this is related to the minimal detectable effect. But at the moment, we're not trying to find what is the minimal detectable effect. So far, we're only saying, if I do an A test and I do a big hammer slash on one end, I can hear something moving. So it's not the minimal detectable. There's clearly the same intuition. I get like, we had minimal detectable effect 20 slides ago. Why is it not mentioned? But you sense there's something there. So minimal detectable effect is typically something you compute before the test starts. This is something that requires a bit more processing. So minimal detectable effect is a theoretical computation, and this is going to be based on large-scale simulation. So you thought that was fun to do one test, and then you do it 100 times as an A test, and you do it 100 times, and then you hammer increasingly hard 20 times. So you start seeing that this is getting kind of a big process to give you those values. But those values, we definitely understand those are random. The 14 is going to be 7, 8, 12 next time. Same thing for all the values. So there's a curve, there's a trend, but that trend is random, essentially. The minimal detectable effect is a theoretical computation. You get that difference, but clearly the intuition is very much there. So far, everybody follows. A test, big hammer on one and a half. See if there's something that makes noise. So far, that makes sense? Does everybody feel like this is not very efficient? Anybody has a better idea? Raise a hand if you feel like there's an easy way to improve that code. Maybe the code before? Anybody feel like that code is not super effective?
You can do bisect search.
Dichotomy. Sorry. sorry, that was minimal detectable effect. Thank you so much for just basically spoiling my presentation. Sorry. I'm getting a little lost. You apply, sorry, the connection with minimal detectable effect is what you want to have is not just, okay, I'm giving a sledgehammer and sometimes it works. You want to know what is the smallest change you can do, what is the small change treatment you can do that will reliably detect the change. So you don't want to work sometimes. You don't want to work 14% of the time. You want it to work almost all the time. Not all the time, because maybe that's just going to be randomly bad, but at least 90% of the time. So for that, you want to define the minimum difference that is reliably detected. And so you run the same list of steps. You store the list of difference. You store the distribution of that, because actually what you care about is not the individual list in a certain order. What you care about is the actual values. The zeros are here just because Python is behaving weirdly when you have sums. And you define a cumulative distribution. And basically, you take that series, and you define a reliable effect, which is if you do 100 runs, 1 minus alpha, so 90 of those 100 runs. So you say, what is the effect that is the smallest effect where I have at least 90 out of 100 tests that say there's a difference there. So you have the 10 of the minimal of the false positive rate, and the 1%, 2%, how far down that line do you have to go to detect something? And basically, this is just a sort of a version of it. After 100 runs, you've tried to improve by 1%, 2%, 5%. And for 90 of those 100 runs to actually make sense, you had to actually improve, you have to move the treatment by at least 50%. So that gets closer to the minimal detectable effect in terms of intuition. Rather than have just a slope, you have 1 point for that slope that is high enough for you to trust it. This is just code for images. If people care about how to write code in Python, please do not look at my code. I don't know how to do that properly. That took me way too long. I'm slightly ashamed. But this is what it looks like. This is a log scale on the bottom, because I'm a little sadistic. So you have, so that must be, that must be 1%, 2%, sorry. So that must be 2%, 5%, 10%, 20%. And you see at 20% we have most people, but if you want to reach that dotted line of 90%, you have to go as high as 50% chance. So you start having intuition that this 1, 2, 5, 10, 20, 50 line is, at least on the log scale, looks a little bonky. It's not super comfortable, and you feel like the actual number is not 50. The actual number is somewhere between 20 and 50. But because we've used this very blunt scale, it doesn't work so well. So this is a bit too granular because of that threshold thing. What we could do is we could have many more thresholds. 1, 2, 3, 4, 5, 6, 7, 8, etc. That would be a bit slower, but that could possibly work. But there's a way to do that that is a bit more subtle. You could do dichotomies, what you suggested, which is you could have a very detailed scale and go at the bottom, at the end. This is not significant. This is significant. Let's look in the middle. This is not significant, so you're somewhere between here. And gradually find, not explore them one by one with a loop on the list, but actually try to have some smart approach. That would make sense. That would be faster. You have an order of magnitude. You have a power of saving. But actually, it's a lot simpler than that. Go back to the AA test. You have control, treatment, and around control, you have this, if you apply the difference, you have a confidence interval. For treatment to be considered significant difference than control, you just need treatment to be big enough to hit the edge of that confidence interval. And you have control, treatment, and all these numbers, you know them. So what you can do much more simply is to take that thing that would make your tests positive in the sense that it's significant and treatment is more than control. You look at that difference and you just apply that difference to treatment. You don't need to explore either one by one every step of the edge, or you don't need to go through a dichotomy trying to explore gradually. You can simply just take the numbers you have and apply them roughly. Does that make sense? So it's not just a question of hammering increasingly high or hammering in a smart way. You can instantly detect what is the exact effect that would allow for that specific test to be significant. Let's take an example. This is just a random AA test. And thankfully, that test is not significant. You can tell here, not significant. The result is a draw. And pay attention to those numbers. So what we're trying to do is we're trying to say we keep control where it is. So 115 and 199, we're probably not going to change. 121 and 224 are the numbers that define the ratio, the conversion rate for treatment. And what we're suggesting is, can we increase 121 high enough to make sense? So the math that was on the previous one, we basically apply it here. So we find detectable difference the way it was defined. We apply that difference to a test, and we compute the test. So if you look at those numbers, they're the same as the one on the page before, except this one. How much was it before? 121? And now it's 148. That is because we've inflated the test by the sensitivity that we captured there. And if you look what the test is, it's significantly true. And what's interesting is that you see the p is very close to 0.5 because that's where we set it. And you look at the difference, 0.8 is just barely above the significant difference. So we find the minimal effect that actually would change what we're trying to do. Does that make sense in terms of what we're trying to do when we do sensitivity testing? And, well, it's a lot less impressive when I pre-compute all the numbers, but if you actually run the 100 version in the notebook, for those who are following with the notebook, and you run that test, this one is a lot faster. You can do 500 runs without wasting your time. And for 90%, rather than have either 20 or 50%, whichever you draw to the luck, you actually have a much more accurate number. That number might be too accurate, because it's just a random value that is close to the real value we care about, but that one makes sense. So far, so good. People, you understand how we computed that whole process for one A test. But we don't want to run sensitivity for one A test. We've been running hundreds of A tests. So let's just look at the same number, but for 10,000 or 100,000 observations, and you realize that that sensitivity that we've been trying to measure, just like the minimal detectable effect, gets more accurate if you have larger tests. So when we say you want to run a test on a lot of people, but if you want to detect small effects, that's exactly what we're measuring now, again. But rather than have a minimal detectable effect that is based on overall estimation and a theoretical value, this is based on the actual value of the data you have. So if you, in theory, feel like with 10,000 customers you're going to have that much precision, that's great. But this is based on actual data. You can use a company data to put as, you just replace generate events here, and you can measure, okay, with the data from the company for the last 2 months, this is the kind of test that we would have been able to pull. This is the kind of change that we're able to detect with that specific data set. Does that make sense? Anybody has been trying to run that with their own data? No? Well, it's a good thing I put generated data events, otherwise that would have been a lot less interesting. The one thing, though, that's because we have, so the event is set, but we randomly generate 100 or 500 splits. And those splits allow you to define what is the sensitivity. There's an element of randomness. So the 29.8 is one number, but if I rerun the same thing, I'm going to find something probably close to 29.8, but slightly different. So the idea here is to basically run the test, but multiple times. So this is the test. This is a graphical representation for respectively 100,000, 10,000, and 1,000 observations. So you can see more accurate observations mean that you have less of a push to make sense. So the idea here from that is small samples are less sensitive. So far, we're not surprised. But you remember that A tests, if you don't do many A tests, you don't have an accurate idea of the alpha. If you want to measure alpha precisely, you want to run 10,000 or 100,000 A tests. It's the same thing for sensitivity. So what you want to do is you want to run sensitivity many times. The best way to do that is to simulate sensitivity 30 times. Once again, do not look at my code around graph. Just it's available if you are. And this is for 10,000 observations on 500 users, the same curve you had in orange, blue, and green. But this time, I've done, for the same case, 30 times the curve. So you see there's still some uncertainty there. It's not perfectly accurate because there's a significant element of randomness. But that allows you to say not just, I think that for 500 users who come on the website 1,000 times, I need to have about 30 or about 25 effects on my treatment for my treatment to be reliably detected. But you have a clear idea of how wide that effect is. So you don't just know how big a treatment you can detect, but also how reliably big that treatment can be. So rather than say, oh, it's around 25, you can say nothing below 30% would generally make sense. The reason to show those curves, even if they're slightly abstract, even if you have to introduce them gradually to stakeholders that are non-technical, is to say you can test on your 500 stores. You can test on your 1,000 partners. You can test on your 2,000 first customers as a small company. All these are perfectly doable. But if you want to run an A/A test, you need that A/A test, you need a treatment to have at least, in this case, 30% more impact than the control. That does one thing that is really, really good for any kind of new company or any company that is exploring a new space, is it says, don't do small changes. Try big changes. A/B test is really good in that case for really big changes. For large companies with millions of customers, A/B test is really good for small changes. But for small companies, what you want to do is rethink your strategy entirely. And that is a really effective way of telling people you want to have bold changes because we won't be able to detect small ones. So the question is, what happens if your test is a little wonky? What about this? What if the A/A test is not around the alpha? What happens if your test is broken in a way? First example, what if you have a lot less customers? Same graph, same process, a little bit of time to compute that. But basically, you go from 25 to 30 to 60 to 80. So if you have 100 users, you probably want to have a change that is about doubling the impact of your conversion. Otherwise, your A test is not going to test it. So it sounds like an A/B test is not a really good idea for that kind of change. But at least you can, for the specific data that you have for your website, tell your stakeholders, this is how much I can detect reliably. Does that make sense? Any questions on the sensitivity test? Any questions on the meaning of those curves? Any question of which case you can use them? Does it make sense for everybody? Is anyone just trying to use the notebook and is stuck? Yay? Nay? Sorry, I feel like I'm just standing between you and a beer, and that's kind of a horrible feeling. Yeah, that's it. Sorry. So if I'm standing between you and a beer, let's just go a little faster. One possible problem is that sometimes the data you have just doesn't work super well. We're going to take an extreme example, 20 observations, which is definitely not enough to run test, and 20% conversion rate, so there's going to be clearly some mistakes. We'll just run a little function that is just basically here to capture errors. We run that, and no big surprise, there's a problem because we don't have the right kind of conversion for treatment. Treatment has no conversion, so of course the code we're running doesn't work. So what we want to do is want to introduce quality check on the segment and the breakdown. So for a given A/B test, we simply define a function is_treatment balance that will give you just a Boolean. You check how many observation in control, how many observation in treatment, and you have this minimum ratio of 40% that you can hardcode and say if we don't have at least 40% of the sample in control or 40% of the control in treatment, decide that the test is not balanced. Another example, if you don't have conversion, control, conversion, and treatment, if either of them is 0, decide that the test doesn't have enough conversion. And basically, I'll put the word balanced. I would have been balanced, and this is the case. So you modify the test with random segment, which is the key method we've been using so far. And rather than just go through assign the test and move forward, so rather than go through that piece of code, you try to check if it's balanced. So you don't think it's balanced. You generate a segment, you run the test on that segment, you compute the value, and you check if the test is balanced. And if it's not balanced, well, if you're verbose, you can output it. But basically, you try again from that loop. So that is a way to hard code controls on your checks. If you're running A/B tests in production, that kind of control doesn't make sense because you cannot tell ahead of time whether or not the balance is going to be true or the conversion rate is going to be true. But if what you're trying to run are A/B tests where you have a small number of subsets, you're probably going to assign them to treatment and control in production. You're probably going to control that yourself. You're going to assign them by hand on an Excel spreadsheet or something equivalent. So that kind of control makes sense. My goal here is to say, if we have that kind of control, does it improve the quality of the test? Well, it allows you to actually have some computation. But as you can see, the A/B test the A/A test is just not very reliable. So that's not something you really want to rely on. And actually, if you look into details in terms of the distribution of the t values or the p values, they're not very reassuring. The reason we've introduced all this long-winded control on how to run tests, what is the A/B testing, what is the confidence interval for alpha with A test, what is the sensitivity test, is because there might be some complication. I'm going to introduce one complication, which is the most common one I've seen doing A/B test is your units have to be clustered. Examples include you purchase have to be clustered by store, those are not by users. You're trying to do some advertising, but the people offline. That offline advertising is controlled by companies who have posters, slots, but they're by city. You cannot buy one poster in front of one of your users. That's not technically possible. So you can only do tests that are at the user level, as you think of it, but actually the assignment to control treatment is at the high level. Typically, in this case, we're going to consider a city level. So you have 100 users, 100,000 users, but they live in 100 cities. The second problem you have, it's not just that you have 100 cities, it's that some cities are really big, like London, and some cities are very small, like Stratford-upon-Avon. There's actually a law that describes the size of cities. It's a Zipf law. And what you can do is generate a function that basically assigns users to cities in a way that makes sense. That's the actual line that does all the work. Because of how that line works, sometimes people are not in the right, if you only want to have only 100 cities. So all that is just basically a correction over the possible anecdotic mistakes of that one. You just process the data so that you have a table user city that has users assigned per city. Then you can generate events with that assignment so that every user belongs to a city, so every event is assigned to the same city. In this case, we're using a zip zeta of 2 just to make the case really obvious. 1.3 is the one that is commonly observed between cities. Language is the 1.8. If you, or there's all sorts of, zeta is a well-known function for lots of situations. And you go through the same generated events, generate segments, but not on user IDs, generate segments on cities, applying the same law. And what do we have? What happens in this case, because you have one city that is a lot bigger than the others, is that you have users in that city that are observation and control for either treatment or control, depending on whether that city is in part of control, treatment or control. This is incredibly imbalanced. The way you can check for that is you can see city number 1 has 600 of the customers and they're part of treatment. So 600 plus 70 plus all the other treatments, you have the treatment section that is a lot bigger than the control section. And for a lot of tests where you have that kind of constraint, that is a real problem you have. It's not just that you have big blobs, it's that those blobs are not of the same size, and you cannot get control and treatment to be of the same size. Does that affect your test quality? Who thinks it's going to completely tank the test? Raise a hand. Who thinks, yeah, no, the test is fine. That's actually not going to be meaningfully impactful. People have no opinion. Damn it, you really want your beers. So you basically force that structure of events into a batch A test, and you run it, and it completely tanks your value. You ask, in which case do you have, what do you do with this A test if it's not matching the alpha value? Well, in this case, you start freaking out because the test by city might not work out. I've purposely taken a very small sample with few cities and a zeta that is completely insane. 2 of zeta is really, really high. It really messes up everything. You can run the same test if you have the code on a zeta of 1, on a zeta of 1.2, and see if actually you have more reasonable expectation for your city. Or even better, if you have clusters on your data, if you have to test on users based on which country they belong to, which language they speak, or any kind of other constraints, that would make sense. And if you look at the T distribution or the P distribution, they're clearly not where you want them to be. The way you see that, well, this one is not too bad, but this is really problematic. This is the number of P's that you want to have a continuous version here, and you have far too few P's that have a very low significance. So what happens in this case is that your false positive rate is abnormally low, which is a source of concern, which means that your test is not doing what you want that test to be doing. You can run the sensitivity test, and you can have a value, but the truth is it doesn't make sense necessarily to run the sensitivity test in this case, because the test itself, the false positive rate is 4. You can tell that because the curve here starts way too low. So your test has other problems than the one you wanted to consider. So I don't think you should run that test in those circumstances. If you were in that case, I would say, I don't think A/B test would work for that subset of users. But of course, if you run the same test with a different value for how many users you have, for how many cities you have, for how high the zeta is, you would have different conclusions. And the reason why this code is accessible for you is for you to run it on your own simulations or your own actual value so that you can understand whether or not your test makes sense in that case. You can try to run the sensitivity test. It's actually not too bad. It's around 30% sensitivity, which compared to the other numbers we have is okay. Actual numbers of actual companies typically are not that bad, but it can happen. But I would definitely consider to challenge that significantly. What we can do is think, okay, we have this data that is not where it should be. You have this big slope on cities. Can we improve the experiment by changing something? And that's usually a very long discussion that you can have between, should we do this because it's going to rebalance the test? Should we do that because it's going to rebalance? Should we have one big city on control and everybody else in treatment? All that kind of tests. I've seen a ton of ideas. I won't cover them all. I'll try to cover some of them, at least one. And the idea is that this whole framework allows you to, given an idea, apply it to the segmentation, see if it makes sense. So you have this test with random segment, modify with the balance. You have another one I'm going to do now. All these ideas, you now have the code to actually run them if you can just modify the segment. What about excluding the largest city? Who thinks that's going to improve the test? Raise your hand. One shy hand. The other one is yawning. Not a lot of people expect that to be any meaningfully different. Let's just exclude that. That's basically equivalent to that. There's two ways of implementing that. It's slightly better, but not meaningfully. It's not good. And if you look at what's the impact on the sensitivity rate, it completely tanks the sensitivity rate because you have far fewer people. It rebalances a little bit control and treatment, but not significantly. So that typically is a suggestion I've heard a lot. It doesn't really help the test that much. Other option that I've heard, schoolyard picking. So rather than have a random assignment between control and treatment, you pick one in control, and then you pick the other, the second city, and you assign it to the other one, just like people deciding on teams on a schoolyard picking. That is a really good idea to have as balanced as you can teams between control and treatment, but it has a massive issue for the kind of approach we have. It's not random. With a set of cities of a certain size, you will always have the same cities in the same control. So you can run one A/B test or one A test, or two, or you won't be able to run a third one with a different subset. So it will not give you some good insights on sensitivity testing because you don't have that element of randomness. So interesting intuition, but not usable in this case. The third one, and I'll stop on that, is a suggestion that you start with a random test and then you swap them to optimize the test as much as you can. I've seen a couple of implementation of that. I've tried to do them. The code gets really unwieldy really fast. But if you want to have an exercise, that's a really good exercise of try to, given a segment, define a swap function that does that. Modify the test with segments, including that swap function, in case you believe that the test is not balanced enough, and see if that actually improves the test. So far, I haven't seen anything that is very conclusive for a test that is not really great. But if you can improve the test sensitivity a little bit, that's definitely something that will be very valuable because you will be able to run a lot more tests. Overall, what we try to do is we try to say you can test on small samples. The examples I took were quite extreme, which is why they're so scary and which is why the tests usually have this completely insane sensitivity of 30%. Actual examples of fairly small samples typically go around 3%. That's the kind of numbers you've seen in some cases. But run extensive A and sensitivity test. It really helps your stakeholders to understand how A/B testing work. They get the sense because you can pick examples of every single, they have thousands of examples to learn from to understand how it really works. And that really, really helps. You can try to find tweaks to improve the segmentation, to identify the clusters in a certain way, to slightly tweak. But those tweaks will be informed by the same A and sensitivity test. So having functions that allow you to compute that is really helpful. One thing that is surprisingly difficult is to find the relevant unit. It's not necessarily a user. It might be a logged in user, but not a non logged in user. It might be neighborhoods and not cities. It might be people of a certain households rather than individuals. That kind of distinctions is something that can actually have significant influence on your sensitivity test. Think about those cases. Try to build simulation with those cases, and you'll be able to find the best experiment format for the best significance. And more importantly, control for everything you're doing before you run the test. Once you have a test, it's a lot harder to challenge the test. But if you have, before you get the results, telling people the test will not be usable in certain cases is a lot easier to do. Any questions on A testing? Yeah.
Yeah. The segments you picked that is treatment was too high with number of treatment. Can you do a sampling of some sort to downsample them and then bring people to the control and then test it?
So your question is, if you have clusters that are very different in size, can you subsample them? Right. That's an excellent idea. Try. You now have the code on your computer. You can actually say, okay, let's try to have for the cities that are largest subsample and see if it actually improves the test. That should be 5 or 6 lines of Python. So just if you want to do it, you have half an hour to go through it, and I'm sure that will actually be very interesting to see if it makes sense. I've tried in certain cases. Sometimes it works, sometimes it doesn't. It really depends on other factors of your data set. Most likely correlation between city size and conversion rate. Any other questions on a test? Sensitivity? Yeah?
I'm not an expert on frequentism in general, but
Yeah.
I guess sensitivity test isn't a different way of doing the power analysis, like sample power analysis, like a beta?
Yes.
Okay.
It is a pragmatic way of doing power analysis.
Okay, but they try to detect essentially, you try and see what your sample size has to be in order to detect an effect of a certain magnitude, right? They both do the same thing.
Yeah.
Okay.
So it's to do that with with an existing sample.
And why is the standard methodology not pragmatic for calculating
It relies on assumptions about the structure of your data. The beta assumes that you have independence between variables and things like that. That may or may not be true.
Also, the t-test assumes a lot of things as well, right?
The t-test assumes a ton of things. Yeah.
Okay.
Which is why if you feel like you want to use a different method than t-test, it's just a plugin. There's actually on the repository, there's an open issue to implement a Bayesian test. There's an open issue to implement a sequential test. We'll be happy to do that. We just haven't had the time before this presentation, but absolutely.
Can I ask another quick question, actually?
Sure.
I was wondering, have you faced any issues, like by using p-values for making decisions on, like, if a certain treatment is superior to a...
Yes.
And what do you do in cases where you have a really, let's say, big effect, detected effect, but a really big p-value as well? Like, if your p-value is 0.06 or 0.11, but you have a big detected difference, what do you do in that case?
It is extremely common. I've done that so many times that I don't want to do that. Like, I'm trying to avoid that as much as I can. So the situation is very simple. You have whatever's the metric that has a lot of uncertainty, and you detect a really big change, a lot of money that a test seems to be saving, but because you have so much uncertainty, you're not convinced this is significant. And if you're talking to people that are not statistician, frequentist Bayesian, so they don't have this intuition of uncertainty, they're like, there's like 40 million on the table. Why are we saying no to 40 million? So I'm like, it's not 40 million. It's somewhere between minus 50 million and plus 120 million, which is, it's a lot of money either way, but there's a big chance that actually we're losing a lot of money if the test is not happy. So what we're trying to do is we're trying to make that situation as painless as possible. This approach tells you, before you do that, tell people any change that is less than 100 million will not have an impact we expect. So that they start thinking 40 million is not a lot of money. It's a weird mindset to change, but if you give them those numbers and you have them focus on the conversion rate, which is a lot less scary than $1 million, you can actually just change that mindset a little bit. Second thing is, do not say 40 million. Show the confidence interval, show the distribution if you're Bayesian, show them the uncertainty as a key part of the result you have. That just avoids the conversation around, I'm only looking at one number, that number's positive, and I'm not going to look at the uncertainty on that number, which is another way of looking at the same kind of thing. P-value is counterintuitive. I have yet to see people who like p-value and can explain how it is. Most people who can explain how it is don't like it because they don't think it's an intuitive way of explaining what it is. I'm sure someone actually likes it and I know how to explain it, but typically that's just not a great overlap. That's why I'd rather talk about those examples. If I can walk someone who has, there were some stats at the beginning, just out of mercy for people, but I can actually walk someone through the whole process without using a single square root. And that is a lot more convenient if you're talking to people who do not like math as a cultural background. I've run a lot of those tests for video game companies. People who make video games are awesome, but not a single one of them was good at math in high school. They make amazing math, actual math. Like, you have a ton of math making video games that are really allergic to that kind of communication. So you want to have something that is colorful, playful. Not a lot of drawings on that, my fault. Tried a new presentation format, but that's definitely the kind of thing you want to do. The last thing is, the problem is if you tell someone either you accept the test because there's 40 million on the table, or you don't accept the test and you're losing those 40 million, is you showing them a dichotomous situation. And that, I think, is the biggest mistake. It's not necessarily not communicating around uncertainty, is confronting them to a yes or no question that seems bigger than themselves. And that's, I think, the real issue around people focusing on the amounts rather than p-value or not understanding p-value. It's not really understanding p-value that is a problem. So that's why with João Martins, we've implemented a sequential test where the decision is not either you take the money or you walk away from it. You can wait one extra day to have slightly better interval. So it's not just we representing tunable on 40 millions, is we say, but if you wait 1 extra week, that interval is going to be slightly smaller. That interval is going to be slightly smaller. And hopefully, at some point, that interval is still quite wide, but entirely positive. So we don't know if we're saving 2 millions or 80 millions, but we know it's a positive number, so it's a lot easier to say, let's go with that idea. Hopefully, we're actually saving the company 40 millions, but that uncertainty is dwindling because we have this sequential approach. The last one is you don't say 40 millions because you randomly stumble on 40 millions. You say 40 millions because the ideas you have are insightful. The change you made is actually meaningful. And there's probably a couple other 40 millions behind that idea if you understand where this idea comes from. An experience I've had a lot in any company I've worked for, and that's a long list, is those changes are correlated to something that makes sense. Improving, like storing someone's credit card number so that if they buy something a second time is a really impactful way to get people to convert more. It doesn't work on people who haven't purchased before. If you think about it for 2 seconds, that's completely obvious. But even things obvious like that, people don't remember them. And actually detecting, saying, OK, we're going to run the test as it is, but we're also going to run a shadow test on people who've logged in for the first time versus people who've purchased something before. We're going to run the test on people in certain countries. We're going to run tests on people who use mobile versus desktop. We're going to run the test in different dimensions. And we're not going to use those as decision makers, but as insights. And not telling someone, oh, it's 40 million saving for the company, but it's 60 million on people who use mobile and minus 20 million for people who use desktop. That is a lot more interesting conversation to have because it's not, I'm telling you to not implement that feature. It's me telling you, you should implement that feature, but not on desktop. And that is not an intuition that necessarily people have because they're just so many dimensions that they don't explore them one by one, but as automation system, you can actually easily check those by yourself. And that turns a yes or no question into a iterative question and into an iterative insight. And hopefully that helps people make better decisions without having to talk about you being the blocker for a large amount of money. But that's just a small part of it. Sorry, that was a really long answer to a question that had little to do with sensitivity tests. But I'm standing between you and beer, so I'd rather make the thirst prolong. Anyone who has a question? Yeah, Jules.
For the last case where we had these clusters with very different sizes.
Yeah.
In a Bayesian formulation, the approach you can use a hierarchical model with shared information between the clusters, which I feel gets away from a lot of these issues with false positives and sensitivity because you're kind of expressing your belief that there is something shared between these cases. But have you tried that out and do you see maybe limitations with that approach or maybe limitations with this frequentist approach when you're trying this type of experiment?
So I'm supposed to repeat the question, but that's going to be tricky. I'm not sure. So, we have users who belong to a city, and you're saying we're assuming that all the cities are the same. There's when you say something shared in the hierarchy. So
yeah. So in like a Bayesian formulation, you could have like shared information between the clusters, which means that if you've got a city with a small number of population, you can actually get a better estimate of the effect by regularizing it effectively with the information from the larger cities. So
yes.
You're not drawing false conclusions about something which has got very small sample size.
That makes a lot of sense. This is something we've been thinking a lot, not necessarily for that case, but for other situations we have. We haven't implemented anything in production yet. This would allow, for specifically Farfetch and a couple of experiments I'm thinking about, would allow us to unblock key situations. The Farfetch price point is very high. It's not a big mystery that we have fewer customers than company with the same revenue. We have very high average order value and fewer customers. And we have a lot of our revenue coming from a small number of customers. Testing on those people is harder because there's just few people who spend hundreds of thousands every month on Farfetch. So this is a key question for us, specifically because of our business model. I haven't found any implementation of that publicly. And I've talked to people at Booking, I've talked to people at Facebook on how they do testing. This is not really a problem for either company. If you know of a company that has that kind of approach, if you know of a lab that has thought about it, I'd be very interested. At the moment, our solution is, as you described, to use larger sample as a Bayesian prior. The information we have on small samples that is an update, and hopefully be able to update that, but we don't have any guidance on that. So if you have any insights, I'd be very, very happy to collaborate on that, just because we are in the dark at the moment. But this is really, I think it's a really good intuition, and this is definitely something we're going to work in the next month. Is there anyone else who wants to delay the beer for everybody else in the room? I can do it, I've got a mic, but Otherwise, thank you so much for your attention. The repo is available for everybody. There's 6 or 7 issues open if you want to do them as exercise. More than happy to talk about experimentation at length, as you've noticed. Thank you so much for being part of PyData. Thank you so much for the organizers. And, well, see you at wherever we're going next.